So hi everybody, I would like to discuss today the following relationship between the probability flux and the distribution of exit point. So this is this YouTube video is part of a series about stochastic processes. So let me start with a definition and recalling the frame for this. So suppose we have a domain and we have a particle, a Brownian molecule, an ion, whatever, started at position x. It follows a stochastic equation, x dot equals b of x plus sigma of x w dot, where b is the vector field. We have here a vector field. And sigma is a diffusion tensor. And so we have seen in previous classes that the distribution of points, so if I take a piece here of the boundary, let's call it d omega, this is the boundary of the domain, and we're interested in the following question: what is the probability that the domain, the process will escape exactly in this part of the boundary? Let's call it the element ds centered at point y. So what's the probability that x at time tau, when the process exits the boundary, it exits exactly at position y plus ds of y, condition that the process started at 0 exactly at x. Okay, so that's the question we would like to ask. Let me switch color. So this is the, so we've seen in the past that this is the probability of x and y. It's probability, let's call this probability density function ds of y. And so what I would like to show today is that this probability can be expressed in terms of the probability density flux. So our mission today is to prove this. We would like to show that p y x is the flux of probability, is the probability flux, is the probability flux. So I'll define in the next slide what is the definition of the probability flux. Okay? So the probability flux, so the solution, we've seen in the past that this density, let me call it Q. So Q is this density probability function, Qy of x. So Q is actually solution of the equation L star Q equals 0. And when we look at the solution of this equation and put a function g on the boundary as boundary value problem, this is an omega, Q has the following expression. So Q of y is the integration of d omega of g of z, and the relation is that we have here gz of y dsy. Sorry, dsz, right? So this j is exactly this quantity. And so now let's show that g can be written in terms of the probability flux. So the probability flux is solution of this equation of L, let's call it P, which can be written minus divergence of J, which is the probability flux, equals minus delta Dirac, and P equals 0 on the boundary, on d omega, and this is omega. So what I would like to prove is that G, Z, and Y equals G, Z, and Y multiplied by the normal derivative at point Y. Right, so if we have your domain, you look at position Y, you take the normal derivative, call it n of Y, and you calculate the flux associated to this equation. Let's call it equation 1. Then we see that Q, that's the Q that we had before. This is this J, that's I call J, Z, and Y, is given specifically precisely by this probability flux. So how shall we show this? We're going to show this. It's very easy, but it's a very important formula because it expresses the probabilities of exit point in terms of the flux of probability, which can be calculated, approximated numerically by running simulations on a computer. So the proof has to do with using the Green's identity. So we'll use Green's identity, and we will write it the following way. We'll say calculate P L star of Q integrated over omega minus Q L star of P, and this is by Green's identity d omega, integrate the same, P d dn Q minus Q dp dn. All right, since by definition we have that L star of Q equals 0, this term is exactly 0. L star of P is exactly the delta Dirac, as we've seen in the previous slide. So this is minus Q, let's call it delta Dirac at point capital Q. Also by definition, P was 0 on the boundary, so this is 0. And so this is the integration of d omega, and Q on the boundary is this J function, G of Z. And this is exactly the derivative, dp dn. So here I have to admit that I'm doing here in the case of B equal 0, otherwise you have to integrate it by parts. For simplicity, I'm not going to do it in here. So since Q is a solution of this equation and the previous equation where we had this G by definition, you remember this was this Q, G of Z, and we had this, I wrote it Q, Z of Y. By uniqueness of the solution, we can identify that Q, Z of Y is this dpdn, and I'm going to write it as if I had made the full proof, minus B multiplied by the normal multiplied by P. So this you have to show. This I haven't shown here because I've used this as if L star was just the Laplacian. Here I have approximated by the Laplacian, but you can show it's more or less the same. And so this is exactly J dot n, J dot normal, which is the probability flux. Okay, so thanks for watching this video, and I hope it will help you for learning this part about stochastic processes. Thanks.